Welcome Code Travel Channel Electronics 101 Transistor. Bipolar junction transistors are current regulating device. The base current IB flows when BBE across the base emitter junction is 0.7 volts or more. The bipolar junction transistor as a current controlled switch and amplification device. Small current flowing into the base terminal controls a much larger collector current, forming the basis of the transistor action. The representation of NPN and PNP, and also the representation of the BCE, BEB, and BCB of the transistor. The large current is presented coming from the collector to emitter, and the small current represented coming from the base going to the emitter. On the other hand, on the PNP, the large current is coming from the emitter going to the collector, while the small current is coming from the emitter going to the base. So, in this presentation of the voltage between the emitter and the collector and the base, therefore, the principle of operation of the NPN and the PNP is exactly the same. The only difference is in their biasing and the polarity of the power supply. In the NPN, the voltage from collector to emitter is positive, while in the PNP, the voltage from collector to emitter is negative. The difference of them are the polarity of the power supply input in the base terminal. Current gain formula BJ-tip transistor. IC over IE is equal to the alpha collector current over the emitter current, and the beta, which is the HFE, is equal to the collector current over the base current. Collector current over the base current, and therefore IC is equal to the alpha multiplied by the emitter current and the beta multiplied by the base current. So therefore, the sum of collector current and the base current is equal to the emitter current. Moving on, example of our transistor switching. We use 100 kilo ohms biasing resistor and 1 kilo ohm load, 10 volts VCC and 10 volts VV. The beta or the current gain of our transistor, the standard from 100 to 200, but we use the HFE or beta is equal to 100. And what we have is the pulse signal on our base 20 Hz. And this is 50 milliseconds per cycle. This is the representation of the diode analogy of the NPN, and on the other side is the PNP. Let's move to our simulation. A simple transistor switching circuit. We have the output in this side, the BCC, which is 10 volts, and our input and our bias resistor control the current on the base. And then we have also here the PNP with the same inputs and the same values that we have in our NPN. Now, for the NPN, the majority charge carrier is an electron. So the electron flow is from emitter to collector. So current flow is from collector going to emitter. The yellow one going down. In PNP, the holes is the majority charge carrier. Stop, remove. Let's put here view scope on our input and view scope on our out. Start, reset, input, output, and stop. So in the first pulse, we had the 10 volts, our input, and on the next 8 milliseconds to 40 milliseconds, because we have 20 Hz and 20 Hz is 50 milliseconds. We start from this ordinate going to this one cycle, so it's 50 milliseconds. And then on the pulse is 8 milliseconds here. Turn on the signal 10 volts, and then after that it goes to 0, off condition. So 1, 0, on, off. And our output is 600 millivolts, and this one is off. So meaning to say, this one is on, our output is 600. Let's start to see the output. This is our output, 631 millivolts. 93.7 microampere is the base current based from the Kirchhoff voltage law in a closed loop voltage network. Equate to 0 the voltage drop, which is the 10 volts minus the 0.7 for the BVE over the 100K resistance is equals to the 93.7 microampere. IC, which is 9.4 milliampere, is 93.7 microampere multiplied by beta 100 is equal to 9.4 milliampere. And then the 631.8 millivolts is 1K multiplied by 9.4 milliampere is equal to 9.4 volts. So 10 minus 9.4 is equals to 631.8 millivolts. So that is our on value, which has a current of 9.4 milliamperes. While if it's off, output will become 10. There is no current flowing. Start again and to see what is off. So this is off, so no current, and then we have an output of 10 volts. Let's proceed to PNP, and it has the same value of our input. So erase, remove our oscillogram and viewscope our input here and viewscope output. Viewscope on our output of the PNP. The majority carrier on our PNP is the holes. Voltage from collector to emitter is negative. Run, start, reset, stop. Input is 10, high 0 volts here. And then next cycle goes down to 0 volt, high output, which is 9.4 volts. So 10 minus 0.7 is roughly 9.3 something. For both of the NPN and the PNP, when IB is equal to 0, the transistor is off. While when IB is quite small, the transistor is partially on. While when IB is increased or more, the transistor is in a full on condition or saturated condition. Now let's change the value of our input, 5 lower value versus the BCC. Reset. So this is our on and off. On is 5 and off is 0. As you can see, stop. So our on is the on output is around 4.4 and our off output is 9.4. This is how the transistor works as a switching process. Let's change again this one to 1 volt. The 1 volt input, we have an 8.4 volt turn on output voltage. And then our current for the 1 volt input is 83.7 microampere. Also change the value NPN with a 1 volt. And then change this one. Viewscope or our output. So they have the same 1 volt here and 1 volt also here. As you can see, they have the same function. Notice that the difference on the on and off is the current on the base, while here is 93.7 microampere and 83.7 microampere, while here is 4.4 microampere in the on and 0, no current in the off condition. That's all, electronics enthusiast. Thank you very much. Mabuhay tayong lahat. Bye. Code Travel.